Hey there, Calculus fans. Another viewer has challenged me to an integral here. This one, if I'm reading theirs correctly, as I said, I'm more focused on techniques to make progress in an integral. I try to emphasize to my students you don't have to be clever to integrate. There are times when there might be a clever technique to get you there faster, and there are very special cases where that might help. But most of the time, it fits our techniques, or we're going to do a substitution. And chances are, if it's a messy problem, a substitution is the way to go. Now, in this case, my first substitution thoughts would be, what about if we do cosine? The only downside of that is when you take the derivative, so if you think about this, we'll do a little thought experiment here. If you take the derivative, you're going to get a negative sign, so the sign's going to cancel, you're going to have this du, but you're still going to have a sign sitting here. And you can say sine is the square root of 1, so it's but that's kind of messy. You're going to run into the same problem if you pick sine. You're going to run into kind of the same problem if you pick sine and cosine. So that leads me to anything else I can do. So if I can't do that, is there a way I can simplify? And so this is maybe clever, but my next thought is to divide top and bottom by cosine, because I think then I can get it all down to one trig function. So that is a little more clever. Sine over cosine is tangent. I just have a feeling, based off of the look of this, part of my challenge is that I had sines and cosines and they weren't all canceling. Now this still doesn't look that great, but let's just take a peek at where it goes. So simplification and substitution are sort of your always to try techniques. Now the moment I see that, I feel like I would like to do t is equal to, and my students know that if I'm at the beginning of what appears to be a long problem, I like to use t instead of u. Keep u in the safe deposit box. So this sort of looks like it's going to work, because then the numerator is just going to be t minus 1. But the problem is the derivative. dt is going to be secant squared of x dx. But this looks a little better because secant squared is 1 plus tangent squared. So it's 1 over tangent squared plus 1. So I'm skipping a little bit about identities. I won't do a full review. But tangent is t minus 1. So to me, at this point, we have it. Meaning it looks like a partial fraction. In fact, it's already in a form where we could use it. Yeah, that's an irreducible quadratic. So at this point, I would just start doing partial fractions. If somebody gave me this problem, again, is there a better way? Probably, but I would write a over t plus, it turns out it's often better to do partial fractions in this factored form, meaning instead of writing bt, this is something you find out more when you take like a differential equations course or you're doing Laplace transforms. It's typically better to write it this way than to write bt plus 1. It is possible to do it either way, but so then I would find a, b, and c. If we cleared that, the a you can find quickly using the cover-up method. If you plug in a 0 on top and bottom, you get negative 1 over 2. So you're going to get negative 1/2. But the other ones usually have to do a little more work to find. So this is going to be negative 1/2 times this mess, t minus 1 squared plus 1, plus b, t minus 1 plus c, all times t. Okay, we need the two sides to be equal. Anything I can quickly deduce. So there's going to be a bt, a minus b, a plus ct. And then out of this, there's going to be a bunch of stuff. So this is going to be negative 1/2. There's going to be a t squared minus 2t plus 1, which is 2. So now let's compare coefficients. This should have been a t squared. This should have been a t. So how many t squareds are there? Well, it's negative 1/2 plus b on the right, and it's 0 on the left. So b has to be a half. Okay, we got that one. Let's do the next one. Now we need c. Where does c appear? It appears in front of t only. So let's compare the t coefficients. On the left, it's 1. On the right, I have a 1 from this times this. And then I have a minus b plus c. So the 1's cancel, and I get c has to be b. So this is a half. Okay, so let's assume I did that. I should do more checking, but I'm trying to get through. I got hung up on the previous integral the student asked me, but this one looks like it's working at a first blush. Okay, so minus 1/2 over t. Let's just take a half all the way out. So we have minus a half, minus 1 over t dt. We'll do that one. I guess we'll just split it up right now. And then there's going to be plus the integral. We'll put a half here. And then we have t minus 1 over t minus 1 squared plus 1. Maybe I'll split all of them up. And then we have plus the integral of 1 over t minus 1 squared plus 1. And I think we have it. So this is going to be negative 1/2 the log of t, and t is tangent of x plus 1. This is going to be 1/2. This is going to be then 1/2 the log. This is one we do a lot in those sections, so I'm not showing the steps on how we get that. Not dt, what am I doing? And then lastly, we have arctangent. So then we have arctangent t minus 1 plus c. That one was much nicer, assuming I did all that right. So negative 1/2 the log of tangent x plus 1 plus 1/4 the log. I guess we could probably put those together in some way. But then there's, the 1's cancel, so this is just going to be tangent x squared plus 1, and then plus the inverse tangent of tangent x. Is it just x? So it's just x. So maybe this is even better. So probably if you looked online, it would be like x plus a half. They're going to factor out a half, and then they're going to write this as a square root. Oh boy. So there's a whole bunch of simplification here. You could write log of the square root of tangent squared plus 1 over tangent of x plus 1, but the top just becomes secant plus c. Could that be right? So is this x plus 1/2 the log of secant x over tangent x plus 1 plus c. Could it really be that nice? Let's give a Wolfram Alpha a try here. See what it says. Sorry about that. So Wolfram Alpha, how do you do with integrating sine of x over sine? It's going to write it in all sorts of ways, so we'll see what we find here in a second. It wrote it that way. Sine of x plus that. There probably was a clever identity that gets us there. Is mine equivalent? 1/2 x minus that. Secant is 1 over cosine. I don't know if that's quite the same. Probably have a mistake somewhere. I'm going to post it anyways. Find my mistake. Let me know where I went wrong. But I hope I'm illustrating this idea of ultimately it's substitution. Even these messier integrals, it's because of what's happening somewhere, especially in there. But I think, for the most part, substitution in our techniques handles a lot. So I hope that's interesting.